grades on the second test were reasonable. So there are a couple of individuals who didn't do as well on either one. Most people are keeping up with the homework, right? Continue to keep up and do the homeworks, right? For example, I may have mentioned this in the first week or so of class. For the couple of people who have not done as well in the first couple of exams, it is possible to pass this class while still failing every test.
Wait.
Right? But, this is a big caveat, right? In order for that to happen, you have to get really close to passing, right? You're basically looking at scores in the 50 range, 55 range for passing, on average, right? Because if you've got a homework grade, keep all 8 homework, keep doing homework. You've got a homework grade about, say, 90% or 90%, 90 points, right? Out of the 100 when you average it out. You drop one of the lower. So you've got a 48 or a 46 on your lowest test, right? But your other test scores are like 50, right? 50 plus 50 plus 50 is 150. Plus 90, right? It's 240, right? 240 divided by 4 is 60, which is passing the class, right? So for example, you can possibly pass the entire class if you got your test grades averaging about 50, a little bit higher, 55 would certainly help, right? And your homework grade's very high. But you have to keep your homework grade high, right? If your homework grade's only an 80, your test grades have to be that much higher, proportionally, right? You all know what an average is at this point, right? You better know what an average is at this point. The final grade for the class is an average of top 4 grades, right? And the homework grade hopefully be one of the higher ones, so you can drop out of the lower test. My point being, if you have not done as well as you would like on the first 2 tests, one of them can potentially drop, right? And as long as you do better on the next 2, and at this point everybody in the class is within this range, right? Everybody in the class is within the range of passing class, given the numbers I just described them, right? As long as you stay at least in the 50s, right, for your next 2 tests, if not higher, and the homework grade's high, you can still pass this class. Okay?
I'm confused, right?
But you'll be squeaking by. Why are you confused?
I don't know if you're giving hope to people in that situation or encouraging people to slack off that's trying hard. I don't know.
Well, keep trying hard, because if you're at the top of that distribution, right, your average score, given the variability, for example, given the standard deviations around your scores, right, is getting narrower and narrower around a grade, right? So, for example, if you got something like an 88, an 87, and a 91, and your homework grade's a 90, right? You drop the 87, right? You're going to have to get at least that 88 in order to get the A for the class, right? You don't have a lot of leeway in terms of how the last grades come in, given the earlier grades, right? To get a specific grade. Right, so it does give hope even for people at the top, but that means you got to work a little harder for that extra point just to get the A instead of the B.
Okay,
right?
I got you.
Yeah, you're going to pass the class. You're going to get at least a B because nothing's lower than a B. But the question is, how hard do you want to work for the actual A?
Yes.
Right? Does that make sense?
Yes.
There are some of you in the class who, at this point, 2 A's on the first 2 exams and solid A average, if not higher than a 20, because there have been a couple extra credit points you could have gotten on the homeworks. This point in the class, there's some people who might actually average right at 100 or more in the class. Right? On this test, there's one person who got 100. Right? One person got everything perfectly correct on this test.
Call them out.
No. That would be entirely inappropriate.
It would.
I'm going to brag on you because that's crazy.
Yeah, that's
because
they
got
got 100?
Yes.
Are they here today?
I'm not going to say that.
I just want to give them praise. Whatever you want.
Wherever you are, that's crazy.
No, for
That's
real.
very good.
That's excellent. Great job. Keep it
For
going.
the same reason anybody who got the lower grades doesn't want me to call them out, I'm not going to call them out high grades either.
Reveal yourself.
No.
Oh, so you're not going to let them reveal
No.
themselves if they want to?
That would be unethical for you to do that. If they want to brag in the privacy of their own life, they can, not in the classroom.
Dang, 100.
All right. Any question on the exam?
No.
All right. This is important. The third exam,
My gosh.
2 weeks off.
Oh, okay. I thought
It's
for some
coming
reason
up
I thought it was
quickly.
next week.
All right, not next week, week after.
Thank
So
God.
we've got tonight and next week,
Okay.
and then the third exam.
Okay.
Between now and the third exam,
Watch me forget again.
we are going to be doing some more, well, it's intellectually complex stuff. The math is simple. The equations for the next couple sections, tonight and next week, the equations are simple, right? How to apply them, how to use them, how to interpret them. That's where the difficulty comes in.
Okay.
For example, last class, we extended z-scores. If I have a simple z-score for a sample, or a simple z-score for a population, I have those equations, relatively straightforward, easy equations. Last class, however, we expanded to the sampling distribution of the mean. Our z-score becomes slightly more involved with one more number, but it's still a simple equation, right? Here's the population mean, here's the population standard deviation. You take a sample of a given size of n, you know the size n of the sample has a mean, you can calculate a z-score associated with the sample, right, which we did last class. We did a couple examples using IQ and a couple examples using height kind of stuff. But you can essentially take, essentially answer the question, what is the probability of a group of individuals sampled from a larger population that you already know the data for, okay? What's the probability of getting that sample from a larger group? Okay? You calculate the z-score the exact same way. The interpretation, going to the table, using the B column and the C column, right? Getting a particular z-score above this point, below this point, works just like these we've already done. Right? Give some good practice on that on the homework I'm going to give out tonight. Any questions on z-scores? So that's called a sampling distribution of the mean. We're going to see yet another variation of a similar formula. You might anticipate it, right? Given it showed up as one of those possible formulas you didn't use on the exam. And given this kind of setup, right? If this is using population data, potentially, I can have something set up like that. Instead of being sigma, I'll use S. That's, well, this is anticipating for the future. This is going to be the very first thing we do after the test in 2 weeks. That's going to be called a T distribution, not a Z. Right? So we'll come back to that in the variations of the differences between that and Z-scores. So that's coming up in a couple weeks.
So we don't actually need to know this right now.
Right now, no, but recognize you're going to be extending it. So yes, you are going to have to know it. Why not know it now?
I guess so.
Is your brain?
It feels
Yeah.
overloaded if I need to only know what I need to know.
You know who Gary Larson was?
Who?
Gary Larson.
Oh no, I thought he said Daniel Larson. That's some crazy method on TikTok. Go ahead.
Gary Larson was
No.
I think he's still alive. He's a cartoonist. He's most famous for doing a cartoon called The Far Side.
Okay.
It's usually a single panel cartoon. It's got little usually animals like cows or monkeys or whatever. There's one that's a lot of cartoons with kids. In one of his little cartoons, one of the more famous ones, it's a cartoon little classroom, right? And all the kids sit in the classroom. There's one little kid kind of in the center room. The kid's got a smaller head than the rest of the kids.
Oh, are you saying that's me?
No, I'm saying the kid basically says, "Hey, can I be excused? My brain is full."
Oh.
Right? As if your brain could fill up.
Okay.
Right.
But seriously.
Your brain
it feels
cannot
like
fill up. You may as well learn it now.
It feels like it.
No. You can always acquire it.
But you can be overwhelmed and like have
Does
a brain
anyone want
fart.
a lemonade? They didn't make me a strawberry lemonade. You know, my first time get my order wrong, so it'll be cool.
It's from Chick-fil-A.
All right, so I'm going to make a point that's going to show up at the end of class next week.
Okay.
You will need to know this. It's going to show up next week, right? But it's going to put the information tonight with the information
Okay.
next week.
Sounds great.
Here's my z distribution, mean of 0, right? Got some raw score, x associated with it. Suppose I take a sample, right? It falls somewhere out here. And it's got some percentage associated with it beyond that point, right? Let's say that the probability of that location, right, is very, very small, right? So the C region here, let's say, is something like a 0.0001.
Okay.
Okay? The probability at random, right, that this mean, as a sample mean, shows up is 1 in 10,000. Okay? That is so incredibly unlikely that you are, instead of saying, well, that was really random, right, you are more likely to conclude something unusual is happening in that case. Keep that in mind. It's going to dovetail with information we talk about hypothesis testing next week. Right? It's going to form the whole linchpin for inferential statistics. Right? Start making decisions. You start evaluating numbers. right? As a quick kind of example, overlap with what I talked about last class, if I come across 5 people, right? Let's say the 5 people have an average height of 6'2", right? I ask the question, is it more likely those 5 people were drawn at random from the population, or there's something unusual about those 5 people?
You're on a basketball team.
Like they're on a basketball team, or alternatively, a volleyball team.
Yeah.
I once walked into an elevator, we were at some other convention, walked in an elevator, and there were like 4 or 5 women got in the elevator, and they were all 6 feet tall.
Oh my gosh.
So I'm standing there looking up these women. And I asked them, basketball or volleyball? It's a volleyball team.
Yeah, that is true.
You know, the odds that 5 people are all 6 foot tall, and women at that, you know, just stepping on an elevator randomly is incredibly unlikely. It's way out here beyond this.
How did you
Right.
feel?
How did I feel? I didn't feel anything.
She was like, because you're looking up at them like. Some guys have like that Napoleon syndrome. Like when women are taller than them, they get all fidgety and stuff.
I don't.
Nervous?
Yeah, they get nervous.
Seriously, did you ever imagine me being nervous?
No.
No, no.
Yeah,
Never.
No.
You're the one
Alright,
that you probably.
so at this point we're going to start talking about probabilities tonight, right? The whole point of this is there's some incredibly low probability, some incredibly low likelihood outcome, right? That we are going to make decisions about. Right? Given the fact that it is such a low probability, we're going to make decisions specifically about it, right? So we're going to talk about probabilities. First thing we can do is talk about issues, kind of introductory kind of stuff for probabilities. When we talk about probabilities, all probabilities are going to fall somewhere between 0 and 1. Every number is going to be some decimal point representation between 0 and 1, right? Alternately, and it works the exact same way, it's going to be between 0 and 100%. We've already seen this when we looked at the area under the curve of a z-distribution is equal to 1, or if you want to think of it as 100% of the areas under the curve. Right.
Just about to use it the same concept.
Same concept. If you have a probability of 0, that means the event is not going to occur at all, cannot occur, it's impossible. So probability of 0 means the event does not occur, cannot occur, is not even an event. If you have a probability of 100, or 1.0, that means the event is guaranteed to occur. It occurs 100% of the time. Right? All the other numbers show up somewhere in between. Right? If you flip a coin, or in showing examples of flipping coins, it's a fair coin, right? The probability shows up heads, the probability shows up tails, right? Is 50-50, which is a 0.50, 1/2. Make sense? So at this point, a couple things. I use an expression like lowercase p, parentheses a. That stands for the probability of event A. Right? So lowercase p, parentheses a, that stands for the probability of event A. There are 2 ways generally to calculate these probabilities. Right? These are a priori and a posteriori.
What?
It's Latin.
I only know English, Dr. Prather.
A lot of English is derived from Latin. If you know Latin roots, you can understand a lot of words you've never come across before.
Here we are with those P's that look like E's again.
Yeah, for real, that does.
You're right, he does.
Would that be?
Smart
Oh,
mouth.
that's a P. I'll try to draw a straighter line.
All we know is a B.
A priori, a posteriori, right? From the Latin, right? Those come out as before the fact, prior to the event, that's a priori. After the fact, a posteriori.
Okay, post and prior.
Prior post, yes, that's where the Latin comes from.
Great.
If you're going to make a calculation, a priori, that means you know enough about the situation to actually calculate the probabilities as if they're random. Right? You actually know enough about the probability. So for example, if I have a fair coin, the coin only has 2 faces on it, right? And I flip the coin, right? A priori, I can ask what's the probability it comes up heads? Because there are only 2 sides, because you know the coin's fair, you say 50-50, right? If I have a 6-sided die, right? Correct use of the word for a singular is die, right?
Yep.
Multiple are dice.
Yep.
Okay, do we...
So this is a bag of dice. Any one of them is a die.
Mm-hmm.
What are you gonna ask?
Nothing.
Do we need to know this?
Like, is this gonna be, are these terms going to be on the test?
Yes.
Possibly? Okay.
Yeah, potentially. Potentially on the first page of the test, giving you the various assumptions and language and the multiple choice type questions, yeah. If I have a fair six-sided die, there's a six-sided die, whether it's fair or not, I don't know, right? What's the probability I roll the die one time and get a 6?
1 out of 6.
1 in 6, okay? And you could say that a priori, haven't rolled the die yet, right? But you can estimate the probabilities because you know enough about the situation, right? So a priori, change that way. A priori is a fraction, number of possible events that I'm labeling A, divided by total number of possible events. Right? Notice what I am labeling as A could be anything. I can say, what's the probability of rolling a 6 on a 6-sided die? I can also say, what's the probability of rolling a 2 on the 6-sided die? I can say, what's the probability of rolling an even number on the 6-sided die? I can say, what's the probability of rolling a number greater than 2 on the 6-sided die? All of which become A, all of which are calculable, knowing characteristics of the die. Does that make sense? That's the definition for a priori. For a posteriori,
So the
number of
top
events
one
A
is
that occur.
after. Oh,
A priori, I have not done anything in the real world. Right? I'm predicting it based on knowing the characteristics of the system.
and that's the first formula.
That's the first formula.
A priori.
Second formula, I start rolling a die. Right? I roll a 1. I roll a die. I roll a 3. I roll a die. I roll a 5. I keep rolling die, looking at the numbers. Right? If I roll the die, let's say 6,000 times, I record every number, right? I might get something like 1,022 sixes over the 6,000 times I roll it, right? And while that's not quite 1 in 6, it's pretty close to 1 in 6 that I would predict a priori. In the real world, you may get a little bit of variation in your actual numbers. But a posteriori, you actually do it.
Yeah. Prior or post.
Post is you're actually taking data from what you have done as events. Prior is you are predicting those events based on your knowledge of the system.
Okay.
Right? Does that make sense?
Yep.
All right. So notice what I've got here. These are fractions. Right? Probabilities can be expressed as some ratio. Let me just do a generic x over y. Some ratio, right? Like I have what's probably rolling a 6 on a 6-sided die. That will be 1 over 6, right? They can be represented as a decimal point notation, right? So if I take the 1/6 and actually divide that on the calculator, I'll get 0.1666 repeating. Most people round that to 0.17, and that will work for our purposes, right? So the probability of not rolling a 6 on a 6-sided die means I roll a 1, 2, 3, 4, 5. That's 0.83, right? Or 5/6. You can represent probabilities either as fractions or decimal points, or percentages. Okay. For the most part in this class, for the homeworks and for the tests, right? I'm going to want you to end with a percentage. I'm going to give everybody convert to a percentage because the fractions. Sometimes people they simplify their fractions, sometimes they don't, right? So you get things like some people give an answer as 2/8, and someone else gives an answer as 1/4, someone else gives the answer as 0.25, and they're all right, right? But if we all use the same number, it makes it easier to go through and grade. So I want the answer as a decimal point, 0.25. But a lot of the math you're going to be working, especially when I give you the formulas in a second for tonight, the math will actually require the manipulation of the fractions through the processing, through the calculations.
So turn the fraction into decimals?
When you get to the final answer, convert the fraction to a decimal point. There may be a couple occasions where you may want to convert the decimal points earlier, but it'll be up to you. In general, once you work through the fractions, you're going to have to pay attention in a lot of cases to numerators, denominators, because some of them will change one or the other or both or neither. by the end, you're going to convert it to a decimal point. Okay? Which then gives a little more language. This is also sometimes listed as probability of, let's say, well, we'll use one language. We'll say success in total for now. Using here, importantly, the word I emphasize is the word in. Right? So what's the probability of rolling a 6 on a 6-sided die, fractionally, or that's 1/6, which is 0.166, we'll say 7, right? But it's also 1 in 6, right? Saying 1 in 6 is equivalent to 1/6, right? Be very careful, because you will frequently hear another set of language of probabilities where instead of using the preposition in, it uses the preposition to. It'll say things like 1 to 6.
That's a ratio.
Well, it's still a ratio.
When it like.
It's called odds.
Yeah.
Right? These are called odds. And unfortunately, this could be written as 1 to 6, or it could be written as 6 to 1. Right? I tend to prefer the English method of doing this, right? And so I'll tend to refrain this as 1 to 6 against, right? As opposed to the American way of doing it, which would be 6 to 1, right? So 6 to 1 is the 6 is in favor of. I prefer to say 1 to 6, where I'll actually put against over here. But this transit, the 2 is not equal to the in. 1 in 6 is different from 1 to 6. 1 to 6 is equal to the fraction 1 over 7, right? It's basically 1 divided by the 1 and the 6 combined. It's frequently used in gambling to kind of hide the odds so the spectator doesn't know what the basic probabilities are. Right? So the most common place you'll see odds like this listed is in horse racing, where a horse may go off at 6 to 1, right? Horses in 6 races, in 7 races, it'll statistically win 1, lose 6. Right? But in the American language, the first number represents the against, and the second number represents the favor. Right? If you flip it over and you're running horses in Great Britain, it would be the same odds, 1 to 6 against. Right? It's usually low enough that's typically one of the favorites. But you get things like 3 to 4. Right? That's really close. Does that make sense?
Is that kind of like the same like basketball teams where like they win 10 games, lose 2?
Yes. Yeah, same kind of thing. You could look at it in terms of a win-loss, but you have to combine 10 wins to 2 losses, right? Or 2 losses against 10 wins, right? But importantly,
So they won 10 out of 12.
right?
Yeah.
Right. Or they won 10 in 12,
Yeah.
right? Their odds of winning are 10 to 2.
Yeah.
Okay. Make sense?
Yes.
Be careful. Small preposition matters. You may only see one exam question dealing with that, so I'm not going to invest in odds. We're much more concerned with fractional and decimal point notations. All right, does that make sense? All right, so let's go at this point. I'm assuming all of you are at this point familiar with common objects like coins. Coins tend to be 50-50, right? Dice, right? Most of you are probably familiar with the typical 6-sided die, which looks like that kind of thing, right? I don't know if you're aware or not, there are other types of dice. That one's a 10-sided die. There's one. That's an 8-sided die.
Isn't that 12?
It's a 4-sided die.
Only you would have
Are you kidding?
weird.
Hundreds of thousands of people have these dice.
Isn't there a 12-sided die?
My best friend.
That's a 12-sided die.
Yeah, we play those in Dungeons and Dragons.
And that's a 20-sided die. 20-sided
That
die is
too.
most commonly associated with D&D.
Yeah, I play those.
But
too.
all these dice are commonly associated with D&D.
Yeah.
You
They're-
play that, don't you?
As much as I can.
Really?
Well, yeah, I play D&D about once a
She
week.
took the words right out of my mouth.
I used to. But
By
Do they
yourself.
know about your minifigures and how you're in the
Oh, you're in the group, I
record
know,
book?
yeah. The group I'm with, they definitely know.
Yeah.
You got mini figures?
He's in the record book.
No, not yet. I've never applied. I should.
You should.
If I applied, I guarantee I would get it.
Oh my god, you've got like a
Oh.
room of
Yeah, room of Dungeons
Half a
and Dragons.
house, not a room.
I
But
might
yes.
excuse us. What does your wife say?
don't be bothering her.
Yeah.
Look, if she's
I don't
smart,
bother
she
anyone.
leaves him to do it, and she goes and takes a nap.
Right.
without being disturbed.
Yeah.
Some of you may be familiar with things that I have a collection of miniatures that are sometimes used for representative purposes in the D&D game or other similar role-playing games.
So you like.
You don't have to use them, right?
So you like
No.
mini action figures?
Yeah.
Yeah.
They're like little tiny action
And
figures,
you
but
can,
they're
like-
not individually articulate, so they don't have movable arms and legs on them.
Aren't they like an inch tall?
Most of them tend to be about this big.
Oh my god.
They're on- if you're into
And-
miniatures, they're on a 28 millimeter scale.
And you
There are
like,
other scales for miniature, like if you're in railroading. Railroading tends to be an 8 millimeter or a 16 or an 18 millimeter
What is it
scale.
called? Like gnomes?
no.
But
Wait,
did you
no.
did you have your own character that you created
Yeah.
made
sure.
into a miniature
Okay.
Well, you typically find a miniature that is most representative of
of
what
your
you want.
character?
Okay,
At
yeah.
this point in the culture, at this point in the technology, if you want to, there are companies that actually specifically manufacture custom miniatures for
Wow,
Yeah.
okay.
you. Right?
So whenever you play the game, do you just like go through all your things and be like, which one do I want to be today?
Yes.
And you pick
It's
out.
not which one I want to be today. It's which one best represents the figure I want to use, and you use that same miniature consistently over multiple games.
Do you
Yeah.
have a miniature house for them? We'll get you one.
He thought about it when you
I
said it. He
never
was
do
like,
that.
no.
I never do that. No. I
In the
never
dollhouse.
do
If you want,
that.
I'll think about. I may bring in representative examples.
You
You
should.
should. I gotta see it. Bring the
But
ugliest
you know, in terms of these
Yeah,
things,
bring the ugliest ones.
Yeah.
I have to dig through that. I don't know what you consider ugly.
Yeah, because there's like creatures in D&D.
But I've got somewhere in the range of 20,000 of them.
Wow.
Are you
Could
serious?
you? How much money do you think you've spent on that?
I don't know. The current value of my miniatures collection, if I were to get the actual retail, the actual marketable price listed for them, is worth more than my house.
What the heck?
So you better never
Think of it this
have
way.
anybody find out where you live because they could literally just rob you of your
No, they
of
couldn't.
all that.
No, they couldn't.
Why not?
It would take a truck. It would take a
Just
semi.
like
They would have to back a semi into my house and spend about 8 hours transporting stuff up and down
That's
because
how
there's so
much
many
you
you
have?
got. Yeah.
You should
And then
apply
you
for
have to
that
find a
record.
buyer.
Then you have to have a buyer for it, right? You're not going to get that much.
Apply for the record.
I am like so shocked right now. I don't know why. I don't know why I'm
So
so
there's a
shocked.
website you can go to.
Because he's so serious, you wouldn't think that happened.
Not at all.
I thought you have a. I
How
thought
big
you
is
have
your
a
house?
house of
If it's
robots.
half your house, how big is your house?
Is it like how many square feet?
Y'all on subject. We gotta learn. We gotta learn. We already.
I think they're trying to
There are
rob
multiple
you.
different types.
Like,
Sorry.
yeah.
I just asked a simple question. I didn't know it was gonna.
How many
They're trying to
square
rob
feet?
you,
I'll
Dr.
just
Right
keep
here.
my mouth shut.
Are you familiar with a deck?
Yes.
In your generation, most people, a lot of people in your generation may not be familiar with card players anymore.
50 cents.
Super.
I mean, you don't have to be a card player to know what a deck of cards
The
are.
vast majority, the reason I'm mentioning this, vast majority of textbooks in this area, and your textbook you're using is no exception, it will do this, right? It assumes you know the characteristics of a standard set of playing cards, right? But your generation has grown up with everything digitized and on computer, and the closest you've ever come to cards for most people is playing solitaire in Windows.
Wait a minute.
Right.
I oppose. Let's not do that.
Yeah.
Because some of us, you know,
Some
we're
people
born
may have
in
in
the
recent
90s.
years been playing
Yeah,
poker,
I
typically
wasn't
things like
born in the
Texas
90s,
Express.
Some of us were just born
Some
into
of
poverty.
us-
And
Well, no.
Dr.
that's
Fraser
because
said,
they're like
well, you
98
poor
cents.
ass.
Some of us spend their entire childhood playing
My
Rummy
main
with their
point is
grandmother.
my main
Well,
point is this: some people, particularly your generation, have never actually held a physical cards in their hand.
I can't believe
You can't even
that.
say
I know.
your generation. There's different
Seriously,
generations
it's
in
getting
here.
more and more
That's
rare.
sad.
Well, yeah, but
And it
not
has
like
been for
our generation. Our generation ends at what, like 12 now?
Did
They're
you
like
know
12 years old
Warcraft
right
Yeah.
used to
They
send
definitely
out
held deck cards.
personalized
So,
tokens
let's
for the
find
deck
out.
cards?
You're going to use a number of these characteristics of cards to make these kinds of probabilistic assessments,
Okay.
right? Figure out how these things work. So, for example, how many different suits are there in a deck?
4.
4. Right? Name them.
Spades.
Diamonds.
Spades.
Clubs.
Clovers.
Yep.
Clovers.
Blue moons.
We call
Pots
them
of golden
diamonds.
If you're not familiar with this, you might want to take note of these things because these are going to show up later on.
Oh,
So you got hearts, diamonds,
Spades.
spades,
Isn't that
Clubs.
and clubs. Right? Each typically represented like that.
Beautiful.
Which ones are red? Which ones are black?
big? Diamonds,
Hearts
Diamonds are
red.
red.
Spades and clubs are black.
Black.
He's proud of
Right.
us.
how many diamonds are there in a typical deck?
13.
Yeah. Or
You
so.
weren't quite as quick on that one, were you?
Well, I had to think. I did 52 divided
Right,
by 4.
52 divided by
Yeah.
4.
Well, yeah, then I
There are
thought.
13 of
Thought
each
about
suit,
it.
In each, yep.
right? Of those 13, how many are face cards?
3.
Right? There are 3 out of each 13 that are face cards.
Oh my gosh.
There are
you're so
10
good.
numbered cards, right?
Okay.
Yeah,
Most
'cause
people,
Queen,
for our
Joker,
purposes,
and King.
yes, for our purposes, an ace is going to be considered a 1.
Mm-hmm.
There are some
Okay.
card games where an ace is also considered an 11. There are some card games where ace has different values. You
Yep.
can either consider the 1 or the 10. Depends on the card games. For the purpose of us, ace is the 1.
You're really good at poker, aren't you?
Oh, you like that question.
I'm going to show you a couple things in a minute.
Try me.
Okay.
Oh gosh, yeah.
All right. Well, here.
No, I want to play
If you're
you
playing
in
poker, if I say, do you know what a one-eyed jack is? Who knows what a one-eyed jack is?
Yes, the one-eyed jack. He got one eye on there. Some of them got one eye, some of them got 2 eyes.
Well, technically, every card has at least 2, right?
Mhm. One at the
it's
top, one
right
at the
top,
bottom.
One at the bottom.
Yeah.
Oh,
That's
no
a 2-eyed
way.
jack, right? Because if you only look at half the picture, that represents both eyes on the same figure. The one-eyed jack is in profile and it only has a single.
Is he special?
No, not special. There's a one-eyed jack.
I see.
He's shady, isn't he?
One-eyed
Always.
jack.
There are 2 one-eyed jacks.
Oh, cool.
Well, here, it's a little more different. You know what a suicide king is?
Wow,
He's
I'm
hanging
learning
by
all
a thread.
kinds of things.
That's a regular king. The
It's
king
like-
will either be holding a sword or an axe.
Yep.
Oh, so the suicide
Yeah.
is the X.
No, no.
It's a
Take
rope.
my card. Mark my card. If you have a king
Looks like you have
which
to play
holds
well.
the sword where it looks like the sword is behind his head, right? He's holding like this.
Oh.
Suicide.
That's called a suicide king, so it looks like he's sticking the sword in his head.
Wow.
Most people, everyone will say that's a suicide king. The problem is some people will interpret the king with the axe as also being a suicide king, 'cause he's holding the axe up to his head. So
And
2
this
of the
is
kings have
for-
swords.
This is why I
That
play
king has
cards.
the axe. So some people think that's a suicide king as well, but some people may not believe that was a suicide king.
So when you play poker, does any of that matter?
No. Well, it does when people are calling wild cards.
Oh.
If somebody's saying wild cards are suicide kings, they say suicide. Or
Oh,
they say
okay.
wild card is a man with the axe.
Okay.
They're talking about the king with the
I
axe.
see.
Do you go to casinos a lot?
No, I don't gamble.
Really? That's
You're a really good
surprising.
man.
That's surprising.
It won't be surprising once we get through the probability stuff. For example,
Oh, because he knows that you like
The
won't
chances
win.
of winning are slim.
No.
Probably banned from the casinos.
no,
Oh my God.
there's the wrong reasons, right? When you're
Wrong
playing someone
reasons.
else for a game of chance.
Uh-huh.
Poker is not a game of chance. Poker's a game of skill.
Yep.
Right? Poker is a skill game. I don't typically pick poker. I typically play pool. But I don't gamble on pool. Right? Because there are 1 of 3 outcomes. Right? You're playing against somebody. Either they are better than you, right? In which case, if you're trading money around, they're taking your money. I don't want people to take my money, so I'm not going to play against people who are better than me. If they're equally skilled, they have the exact same skill level as me, we play, all we're doing is trading money back and forth, and nobody ever wins anything. Nets out to 0 because they have equal skill. There is equal aggregate. In multiple games, it will average to 0. Right? And then alternatively, if I am better than them, right, which we'll tend to think of when they think of gambling and conning people and running cons and games on people. If I am better than them, right, I am taking their money,
Wow. This
right,
so
which is
bad.
unethical.
It's on
Like,
that. Yeah.
In theory, I see what you mean, but that's not true all the time.
One of those 3 cases must be the case. Mathematically, either I'm better
Yes.
than them, they're better than me,
Yes.
or we are exactly equal to each other.
Yes, but I'm saying
Every one of
that.
them I have a problem with.
Okay.
There's
Well,
some
what if
nuance
you
there.
gamble? What if you gamble like on the machines and stuff? Those are different.
They're better than him.
Ah.
The machines would still.
It's
I don't know how
AI.
I don't know how the machines are programmed, and I have no interest in them.
Oh, because he's non-technological.
No, very technological in a lot of ways. I
But
just have no
you're
interest
you're
in
a
playing
very
against the
ethical
machine.
person.
I found
All right, so
playing the
let's
machines.
do
I
this.
found that you if you win like any kind of amount of money, you walk away from that machine and you go play a different one because odds are you're going to lose that money in the next hole.
I lost $20 in the machine. Found $20 on the way out the
I
door.
need
So
that.
As an example of a point I made earlier, we're going to lead this into probabilities in a second, right? Suppose I shuffle up the deck. And I've been shuffling the deck here for a couple of seconds. So I'm shuffling up the deck. If I ask, what is the probability that the top card is the ace of spades? How many total cards are there?
52.
A priori. How many ace of spades are there in the deck?
4, no?
Ace of spades.
1.
1, yep.
Spades, number 1 out of 13.
Yep.
Right? What's the probability of that? 1 in 52. Right? Which is just a hair under, right? 2%. Right? If I flip the top card, Watson, it turns out to be the ace of spades. Right? That's a pretty low occurrence.
Okay, shut up. I hate you for that.
What?
Well, how did you do that?
Cheated.
It's random.
No, it's not.
All right, here, look. Right?
I know how to do one card trick.
You remember
And if
in
you're
other
about to
class,
do it, it's
you
gonna
showed
make me
us
so
your
sad.
YouTube, you were a magician.
Okay, that's not fair. I just saw you. You just shuffled them.
Yes, I did.
What's the
I'm gonna continue to
probability
shuffle.
of pulling
Good. I'm gonna be a good shuffle.
spade?
What's the probability? King. What's the probability? The top card's the ace of spades.
1 out of 52.
How do you do it though? You're not telling
Those
me
are
anything.
his cards. They listen to him.
Now, just flip the ace of spades twice. Each probability was 1 in 52. If it's a fair deck. If it was randomly shuffled. Right? If it was randomly shuffled, what's the probability I flip 2 aces of spades as a top card twice in a row?
You're gonna show us how to do it.
So
One
then
No,
again,
let somebody
that'd
else
be
shuffle the
2
deck
out
and
of
then you-
104.
That would be
No,
one out
no.
of
That's what I
1
say.
out of 100.
255.
2,500, 2,000.
A big old number or whatever it
It's
is.
well over 2,500.
So tell us how to do it.
Wait,
Right.
you did 52 times 52?
So it's 52 times 52.
2,704.
2,704.
Okay.
So if I'm doing it twice, right?
You just lost me with that. Why wouldn't it just be 52 plus 52?
We're going to talk about that exact issue in a second.
Okay.
Right?
So I'm not slow.
So watch. I like the reaction you're getting. Shuffle them up again. What's the probability the ace of spades on top now?
100% right now.
It's 100%
Yeah.
right now.
No, okay, well, I have come to the conclusion.
Now here's the question. The odds of that is now 1 over 2,704 times 1 over 52.
Right.
Do you think it's random or do you think something weird is happening?
Yeah.
Something weird's happening.
There you go. That's going to be the whole basis of the next 2 weeks. Right? You are drawing a conclusion. You are coming to an evaluation. You are making an inferential decision based on the probability of randomness versus the probability of something happening that's not random.
I don't like this.
The probability of something that's random is so incredibly small, you're going to say, hey, that probability is so small, it's not actually random.
I feel like we haven't
I
learned
would look
anything
for,
in this class yet.
So
Do what?
I haven't.
Wow.
So I didn't hear what you said.
Good.
You don't want to know.
Not in this class. I meant during this class time.
She don't feel like she's learned anything in this class.
In this class
In this
today.
class
It's one
today.
specific,
We're
yeah.
getting more specific stuff. We have time.
Oh, yeah, I'm aware.
So what's the probability of any one card on top right now?
1 in 50.
1 in 52. Right? If I name the top card, say it's a three of clubs. Right?
You're going to stress me out. You just looked at him a second ago. I watched
What's
you.
probably the next card?
Stop!
Hang on.
1 in 51.
1 in 51.
Yes.
Because there's one card gone.
Right.
Okay,
Right?
tell are you
What do you-
are you about to
Is
say
it
what this
though?
card
8
is?
of clubs.
I'm gonna cry.
Cry.
Breathe.
Right?
It's
Let it
okay. Breathe. I'm about to go home and watch YouTube videos on how to do this trick. I can show you how to do one. I know how to do one.
If you're actually in the area of poker and you're playing people for games,
Wait, you do? So you are intentionally you?
no, I don't do this against people. This is illegal. This is unethical. You don't do this is likely to get your knees broken, your fingers broken if you do against people who are actually meaningful playing against real money.
Why do you care so much about ethics?
We don't.
It's to a military base.
But you have
Exactly.
some people, isn't that the same concept?
You broke it
Yes,
I don't
it
play
does.
pool for money. I don't gamble on it. I play for winning.
It's
I
enjoyable.
play for winning, he said. Do you win quite frequently?
Yes.
Yes.
Or he wouldn't play. He would break sticks.
I am better at pool than I am at cards.
Dang.
All right, so now we're gonna get to this.
It's never my turn.
2 ideas. I just showed you, actually. If you were paying attention, you actually learned something that I realized. Terms with replacement versus without replacement. If you are taking probabilities and you're, say, drawing cards out of a deck, right? If I draw a card out of a deck and put it aside, right? I have now changed the probability of successive cards drawn from the deck. If I take out the 3 of clubs initially, right? Well, the odds of that is 1 in 52. That leaves only 51 cards left in the deck, right? That is without replacement. All right? I don't put it back. That's without replacing it.
Oh,
On the other hand, if I take a card, look at it, shuffle it back in, right? I have now reset the probabilities to the original odds, right? That is with replacement. Okay? Those terms are going to overlap with terms we're going to have in a minute called independence versus not independent. All right? There are going to be a couple of terms here in terms of things like independence versus mutually exclusive. Right? Everything I've described so far, with the one exception of the 52 times 52, we've only had a single event. At this point, we're going to start talking about joint occurrences. So talking about 2 or more events. Right? Whenever you have the calculation of some joint occurrence, right? You're saying, what is the probability of 2 things happening? Right? There's going to be an important term differentiation here. Right? You're going to say, what's the probability of something happening, first event, or a second thing? Right? Alternatively, the other interpretation is first event and a second thing. So the 2 big words here are or and. Right? Look for these words. One of the issues that makes this some hard material in this section is there are going to be a lot of word problems. Right? There's going to be a description of a bunch of word problems, right? And you're going to have to put that word problem into a formula, into an equation, right? The words in the form, the words in the expression of it, in the description of the problem, will tell you which equations you are using, right? There'll be some simple forms, but then there'll be more complex because you can add these things together, right? You can create more complex systems of these things. We're going to start off with having 2 possibilities. So we may go to 3 or 4 or 5. Next week, maybe upwards of 8 or 10.
On the test?
It's probably not higher than 8.
And
All right,
it's
so using the word or,
One test grade drop.
this is going to set up the addition rule. Right? So if you see the word or, you're going to use the addition rule. The addition rule, in the general case, we'll leave the cards out for a second. In the general case, the probability of A, notice, or B, those are 2 different events. Notice the parentheses around those events. The addition rule says the probability of A or B is equal to the probability of event A plus is not or, but plus should be equated largely with or, probability of event B minus probability of event A and B. Right? That's the general equation for the addition rule. Look, that's a simple equation, right? There are 3 terms in that equation. Probability of A, probability of B, probability of A and B. Right? You add, subtract them appropriately, you get one answer. Okay? Because notice they're all probabilities, there are little p's next to them. Every one of those probabilities will have a value somewhere between 0 and 1. Does that make sense? All right, so go to my cards example. All right? If I ask the question, what is the probability of drawing, how about a 5, the number 5, or a diamond? Right? If I say probability of 5 or, say D for diamond, right? That equates to the 5 is the A, the D is the B, right? So 5 is the A term, the event A. calling event B a diamond, right? So what's the probability of drawing a 5 at random from a deck?
Oh, so this is 5 or diamond.
5 or, yeah, D, I'll put a little DI there.
Okay.
5 or diamond,
Okay.
right?
Wait.
Or 2 out of 26.
Oh,
1 in 13.
5.
yeah.
It's a probability of 5.
5. But
out
you
of
said 5
52.
or a diamond.
4 out of 52, right?
Yeah.
5 or a diamond. But notice I want the probability of A. Probability of A specifically refers to the 5,
5. Okay.
right? So the first number in this is the probability
Of
of a
five.
5. The
Yes.
second number is the probability of a diamond. The third number is the probability of a 5 and
A diamond.
a diamond.
Okay.
Right? All it does is swap 5 for A and D for
Okay.
B there. Right? It's the exact same equation. Right? So what's the probability of 5? How many 5s are there?
4.
4. A priori, how many total cards?
52.
52. So the probability of 5 is a 4 divided by 52. Right? What's the probability of it being a diamond?
13 out of 52.
13 out of 52. So I already said there are 13 diamonds. Right? So 13 out of 52. Now if you wanted to, you could convert those to decimal points anywhere along here. Right? You could reduce the 4 out of 52 to a 1 in 13. Right? You can convert the 13 out of 52 to 1 in 4. Right? For these problems, I recommend don't do that. Right? Because you're going to be adding and subtracting fractions, and the denominators for these problems, for the addition problems, are going to be the same. You're already going to have a common denominator. It may not be the least common denominator, but it'll be a common denominator, right? And you just go across the numerators and add and subtract them, right? So, last term here, how many 5 of diamonds are there? So one card, which is both a 5 and a diamond in a single card.
1.
There's a single card, it's 5 of diamonds.
Uh-huh.
Right? There's only one, 5 of diamonds. So that becomes 1 out of 52. Right? 4 plus 13 is 17. Minus the 1 is 16 out of 52. At this point, convert to a decimal point. Because that's the end of the problem. Right? And that's not going to have a symbol. You got a decimal point number there. So if I take the 16 divided by 52,
31%.
I get a 0.31, rounding it up to 2. Round these to 2 decimal places, that would be fine. Right? So 0.31. Does that make sense? Importantly here, the A and the B are just placeholders, right? They could be any terms. Instead of saying 5 or diamond, I could say something like, what's the probability of, how about a number card? So a number card, we'll say greater than 7, or a face card. Right? So how many number cards are there greater than 7?
And the whole deck.
Okay.
3 times 1, yeah.
There's an 8, higher than 7, a 9, and a 10. Right? 8, 9, 10. That's 3. They come in 4 possible suits. So there's 12 out of 52. Right? So this is the probability of greater than 7. Don't just put 12. If you put 12, 12 is not a probability. Right? You need a probability of a 7. That's 12 out of 52. A probability is always going to be a fraction or a decimal point. Right? Not just 12. Right? Plus, how many face cards are there?
12.
12 again. It was 12 out of 52, not just 12. Right? How many face cards are there greater than 7?
All of them?
None of them, because they don't have numbers.
Okay.
The way we define numbers, there are 0 there. Okay?
Points on that.
There are 0 face cards that are also 8, 9, or 10. I cannot have an 8, 9, 10, which is greater than 7, and also be a face card.
True.
Okay. Does that make sense? So the answer now becomes 24 out of 52. It's going to be roughly 0.46. We got a calculator.
Very close to half.
That's right.
0.46.
Does that make sense? Let me introduce a term, then we'll take our break. The term I just introduced there without defining it specifically, is the idea of being mutually exclusive. If you see the expression mutually exclusive, right? Mutually exclusive means the probability of A and B equals 0. In other words, mutually exclusive is the two events cannot occur together. Technically, probability A and B equals 0. Right? If I said something like, what's the probability of drawing a card, it's a number card, that is both odd and even? Right? There's no card that's both odd and even. Right? Probably A and B is equal to 0.
So you said A and B can't happen.
If A and B cannot occur together in the same event, right? They are mutually exclusive from each other. Right? You cannot both simultaneously win and lose. I cannot roll a 6 while simultaneously on the die roll a 5. Say what's the probability of rolling a 5 and a 6 in a single roll? I can't do it. Right? So those events are mutually exclusive. Okay? Cool. And one more term. It'll sound similar. The term is mutually exhaustive. Don't confuse mutually exclusive with mutually exhaustive. A lot of times people drop the mutually and they simply say exhaustive with the second one. Mutually exhaustive means probability of A, notice, or B equals 1. If two events are mutually exhaustive, that means one or the other must occur, right? And the two of them are the only possibilities you've got. Flipping a coin, the outcomes are mutually exhaustive. You get the probability of heads or the probability of tails. You're going to get either one of them. It's going to be heads or tails. 0.5 plus 0.5, right? And I can't have a heads and tails simultaneously, so they're mutually exclusive from each other as well. Equals 1. Probably flipping a coin and getting a result is 1.
Is that supposed to be probability of A and B?
This one's or, that one's and.
Okay.
Okay.
Because the or is going to be the addition,
Okay.
right?
Gotcha.
Now notice what happens to the formula then, right? I mean, ditch this for a second.
Oh, that makes sense.
I'm leaving it out. Right? In the addition rule, using the or, if events, I'll abbreviate, mutually exclusive, right? Probability of, that's an uppercase P. Doesn't matter if it's uppercase, lowercase. Sometimes I'll switch back and forth. I use lowercase to be consistent. I just said probability of A and B is equal to 0 because they're mutually exclusive. Which means this term drops off, and you simply have probability of A plus the probability of B. Right? Just like I did with the greater than 7 or face card. Does that make sense?
Yep.
Any question on mutually exclusive, mutually exhaustive? Let's take a break. We're already for it.
So what you just wrote right there is for mutually exhaustive.
If you have two events that are mutually exclusive, right? A plus B, well, A or B equals A plus B. Now, if they're also mutually exhaustive, then A plus B, probability of A plus probability of B, will equal 1. Right? But I can have events that are not mutually exhaustive, but are mutually exclusive. For example, I take my 6-sided die. I say, what's the probability of rolling either a 4 or a 5? Can I roll 4 and 5 simultaneously? No. So they are mutually exclusive, right? If I add up the probability of a 4 plus the probability of a 5, is that equal to 1? If the probability of a 4 is 1 in 6. Probability of a 5 is 1 in 6. Right? Does 1 6 plus 1 6 equal 1? No, it equals 1/3. Right? So probability of a 4 or the probability of a 5, while those events are mutually exclusive, they are not mutually exhaustive because they don't have the 1. I've got other events like probability of a 1 or a 2 or a 3 or a 6.
Okay.
Okay?
If they're both, it kind of lost me on the why it would be 0 back then with the greater than 7 base card.
Say it again.
This is where you
have a card, which is a number card, greater than 7, and that same card also have a face on it.
Okay, so you're
So greater than 7 and face card are mutually exclusive. Can I have both
You're
in it?
not multiplying the.
No, I haven't multiplied anything yet.
Okay.
What chapter is this?
8. What's it, 8?
Chapter 8.
Yes, chapter 8.
Okay, so no multiplying.
Not yet. That'll be the multiplication rule in a second. Right now we're doing the addition rule. There's going to be a multiplication rule following.
So this test is harder or easier than last test?
Tends to be,
Statistically.
over past classes, tends to be a little bit more difficult. While the formulas are easier, right? I don't have a lot of squared and square roots, and I don't have a lot of terms embedded in another term. There are a couple of simple equations, right? Like the z-score equations, the addition rules. There are only be 2 addition rules. One's the general case, one's the specific case. They're mutually exclusive, right? There's going to be a multiplication rule, general case and specific case. There's going to be a binomial distribution. It's all the formulas, right? But the hard part is you'll be given word problems, right? I'll give you some homework on that. Give you word problems, like what's the probability of this or this? What's the probability of this event and this event occurring, right? You have to figure out the baseline a priori probabilities and put them somehow into an equation to calculate the end probability. Translating the word problem into a formula expression, the equation expression, while the equations are relatively easy, that translation becomes an issue. People they don't tend to realize how to flip the numbers, well, use numbers in place of the word problems, especially when you get some of the more complex stuff next week.
And the last test is fairly decent.
Last test will be easier. The last test will only have t-test and de novo on it.
Okay, so
Those formulas, while they're more complex formulas, they're bigger formulas, they're very, very simply implemented. And the results, based on the inferential stuff we're getting into here, are easy to interpret.
Almost
Here.
over, huh?
What?
Almost over.
what do we got? What? 6 weeks? 7 weeks?
Yeah, I'm not liking this. It's a lot. It's a lot to take.
Wait, it's worse.
Is it? You already
This is
know?
the easy stuff.
You want to see a cool card trick?
I love code tricks.
Go
See a
ahead.
cool card trick.
Okay.
You volunteer. In a second, I'm going to have you cut the deck of cards. Right? I'm going to look through the deck. I'm going to pick where you're going to cut the cards.
Alright.
You're going to predict it ahead of time. Right? You know, write it down. So it's differentiating with the black marker here. Let's put it up here. In order to make things more misty, as a WKU tower. You'll get one of these when you graduate.
I got it in my box.
There'll be different logos on from depending on what year you get them.
I went to the spring fair.
There you go. Take that one, cover the deck.
Just pick it up randomly.
Just pick it up wherever you want to cut it. Wherever you want to go. Whoops. Sorry. The deck upside down. That's not going to work. Hang on a second. That's very strange. Oh, that's what it is. Hang on a second. My mind blanked for a second.
He flips them.
There we go. We'll make sure we don't change the numbers around. So we'll reshuffle it. All right. Do the same thing, right? Oop. Find a cut through. Wherever you want. Either way.
Where are you at?
Here, I'll hold on the end so you have the short. So you have the short there. Yeah, sure. Right? Just take that top card. That's where you cut it, right? Then back in the jack heater. And I haven't touched that card, have I?
No. Yep.
You're a
That's
magician.
fantastic trick. Huh?
You're a magician.
That's a fantastic trick.
All you do is hold the card where you want her to put it.
Did it feel like I held? Did you cut it where you wanted it?
Yeah.
I can do it again if you want.
want to try it?
Lucy's not taking our money.
Here, a bill one.
I'm not betting on
It's predicting the future. It's a precognitive test.
I better go to the
Let me get rid
bathroom
of this one.
because after every break, then I have to go to the restroom. Like a kid at school.
There you go. Okay. Cut it wherever you want, right?
Yeah.
Take that, put it up underneath the thing, find it wherever you want to cut it, and cut it.
I have to do it through the towel?
Yeah, just do it through the top.
Oh, okay, that's not gonna be
I was like, what's going on?
There's the top card.
Okay.
I think I've got it. That's not bad. That works.
Can I show you the one trick I know when you're done?
So you see Jack of Hearts?
Yes.
Wow.
That's crazy. That's super cool.
This is really cool.
You like my healthy, well-balanced dinner?
I see that.
Yeah.
Mine wasn't no better. I gotta go to work after
Those are
this.
so good
So you just
though.
missed a really
They
good
are.
card.
Those are
Blow
delicious.
your mind.
I like the white cheddar ones.
Sorry.
You're good.
I just spent so much money.
Don't tell me what it is, show her what it is.
You know what? I can look away. He's doing card tricks. No.
She's picking a card.
Okay.
Right? You show her how you want.
I saw. Okay.
Okay.
Gotcha.
Now, this is a fun card.
You're gonna
I'm
piss
going
me
to
off.
wipe it to the death.
Oh, you already missed
Whenever you
it.
want, tell me to stop. Right? And put the card at that point. Right? Tell me to stop whenever you want. Right, put your arms out. This is where it gets fun.
Why are you looking at them?
So I gotta find her card. Oh, that's gonna be so sweet.
I thought you weren't supposed to look at it when you found her card.
Huh?
You're not supposed to look.
He doesn't know what it is though. Yeah, he didn't see it.
I never saw her card.
He's supposed to pull it off the top.
Oh,
and
shit,
then
I forgot what your card was. Well, he did a different
Well, hey,
trick.
yeah, let's do this way. Let's do it this way, right?
Roll me the card.
Was that your card?
Yeah.
No, wait,
No,
no.
no, it wasn't, right?
Okay.
Hang on.
You little. Oh,
You
you
take
could
that
have fooled
card.
me because I already
I'm gonna put it-
forgot.
What do you mean?
I already
I'm gonna
forgot
shove
what
it
card
right there. I'm gonna slide it right there. Okay? I get another chance. Got
I'm
another
gonna
chance.
cry. That's a short-term memory.
All right, here we go.
I'm sorry.
No, which card was it? Was that it? You sure? Take the card. Put it right there.
So are you just messing up in this part of it or what? No, he never messes
I want
up
three
unless
chances.
it's
I want three
intentional.
chances. 3 chances is fair, isn't it? We got 52 cards. 1 in 52, right?
Come on. Well, then it's 1 in 51 and then 1 in
Right.
50.
Yeah.
Right, which is actually lower than 1 in 52, 1 in 52, 1 in 52. So now, that was my last chance. Alright, so this will be it. Ready? Is that it?
No.
Well, hang on. One of those 3 cards is the one she drew.
No.
Do you want to bet on it?
Nope.
Oh,
Betting is
stop! You're gonna make. Oh my
This is why I
god.
don't bet, right? That's a really good betting trick, right?
Stop. I cannot do this.
It's up there on the top.
Yeah.
This
is not a game.
That's a fantastic betting trick, right? Because you can get somebody, well, it wasn't there, you didn't, and it's there.
There's a lot
God.
of tricks though. There's a lot of tricks where you have to like hide the cards in the palm of your hand,
And I can't do it just because I can't like get
It
my
took
hand
me-
to hide it.
I learned that trick probably when I was about 8 or 10 years old.
Mhm.
It took me about 8 or 10 years in my mid-teen years before my hands got big enough that I could do
Yeah.
it.
Like sometimes I can do it, but. Ooh, Reagan, can I do one? Can I do one to her? Can I borrow your card?
Stop.
I only know one.
Why does everybody want to do it to me?
Because you're fun.
Because you have the
Oh,
best
really?
reactions.
Not really grab camera and me. Thank you so much.
It's not a, it's a very old deck. So
Hold on, I gotta remember how to do it.
Oh god.
Sometimes you have to have very, very new decks that are
She's
very,
gonna
very long,
mess up.
very sticky or whatever.
I gotta remember how to do it.
You're gonna mess up.
Oh, we're not
So.
in Vegas.
can't do that in Vegas.
Hold on.
Right, for one thing, if in Vegas, you're not dealing with single deck.
Sorry.
You're typically dealing with
I promise I'm
cards
not
being
deceased. I've been on antibiotics.
passed out of a
Okay.
shoe.
No, you're good.
Right? So it's a
I
collection
got
of decks.
strep on my
Usually
first
a minimum,
break. I was so
either a 6-deck shoe or an 8-deck shoe or even a 10 or a 12-deck shoe. Right?
There's 3
So
stacks.
you're looking at the general
You
odds based on the large
are gonna
numbers.
pull a
You're
card
basically shuffling
from
like
one of the
12
stacks.
decks
You're gonna
together.
look at it. You're gonna remember it, and then you're gonna put it back
And
down
individual
on any
people
of the
don't have
stacks.
control over the
Okay.
decks. If I had the
Okay.
ability to deal,
So
I
I'm not
would
gonna
play cards like I was doing, right?
You
You can't do that in Vegas.
Okay. Where it is? You can have okay. So.
Okay, hold on.
She doesn't. She's gonna mess it up. No, I can. Okay.
If you get started on it, if I see the
I gotta
decks,
restart
it's
it.
likely that I will know it.
You already know how to do it. I know that. I remember how it goes now. Okay. It was like the lead up to it that I forgot. Okay.
Sure.
So we're gonna do the 3 piles again.
Okay.
What I'm gonna do is I'm gonna make your card come up through the bottom of the table on top of the stack.
Wow, okay.
Yeah. Okay.
Wow.
Yeah.
Okay.
Get ready. It's awesome. Okay.
Okay.
So pick a card from any of the piles and then look at it and then put it back down on any pile.
On any
okay.
pile.
Yes.
Okay, but you're allowed to look
I'm
at
allowed to look. I'm not
You
allowed
just
to know
don't know what my
your
card is.
Yes.
Yeah, that's true. Okay.
Okay. So
Okay, you
remember?
see this card?
Okay, now put it down on any of the stacks. Okay, so to make it come up through the table, I have to hit it. Okay, so you want me to hit it like this, or like this? Pick, how do you want me to hit it to make it come up?
Like that.
Like this?
Mhm.
Okay, so I'm gonna move your card in the middle of this stack.
Okay.
I'm gonna shuffle it up. Okay, I'm gonna shuffle it up real good. I'll even let you shuffle it. You want to shuffle it?
No, my hands have sun chips.
Oh yeah, that probably would be nasty. Okay, hold on. You got Cheeto fingers.
Yeah.
What in the YouTube channel is going on here?
Okay,
No, for real.
do you want me to do it like this?
Mhm.
Okay. Is that your card?
Wait, no, it
She
wasn't.
crazy.
That's not
You
it.
know how I
It
did
is.
it.
That's exactly how you
Yep.
It is.
What?
That is
Did you not
it.
see it?
No, I thought it was
I
three.
didn't see it either. I was looking dead at her.
I thought it was 3.
What
Well,
did you
either
do?
way, you
That was
fooled
the card
me.
you chose.
It was the one.
No, yeah, you're right. You're
What did
definitely
you
right.
do?
I'm not telling.
I don't know how do you see it and I don't? I'm
And
lost.
I'm
Because
right
he
here.
knows how to do stuff like this, and
I
he's
know what
sitting
I'm
right
looking
there,
for.
so he knows what to look for. So he could have saw it easy because my hands are
Do
small.
it
You
again.
guys are a little bit small for that trick. That's not really a trick designed for your hand.
No.
But she
But-
still got me.
She was observant, so it's okay.
I tried so hard. Did you see
You were
it?
too. You were,
You
too
were
interested
looking
in
dead
the
at you.
sunshine.
Like,
You don't know how she did
But
it.
I was looking right at it. I did
You
get
wanna know
Germex
how I
in my
did it?
eye earlier though.
yeah, you want to know?
I know you put it in your hand somehow, but I
Jake,
just
I
don't know
did.
when or how or what.
Okay, we're gonna go get
Okay, hold
Too
on.
interested in your sun chips and you weren't paying attention.
How did you get a WKU towel?
Because he works there?
I have one of them things.
Here you go. Here's the go. You taught 3 little piles.
That's not good.
My papa taught me how to do
3
that.
piles. Right? We'll start with you.
I'm looking.
I'm going to name the
Oh,
top
okay.
card. I'm going to name the top card
Okay,
off each pile before I draw it.
okay.
So you have to remember the first one.
Oh crap, hold on.
It's just one card.
Short-term memory fried.
Just 9 of hearts.
Okay.
Okay? That one.
Cool.
Haven't drawn it yet.
9. Got it.
Let's go. 9 of diamonds.
Okay.
That one.
Okay.
No, I know what you're gonna
There's
do.
2 cards in your hand right now. I saw
Yeah.
Yeah, so
Well, 9 of hearts, 9 of diamonds.
yeah.
Third one's ace of diamonds.
Okay.
We got 3 cards.
No, that's not fair because I know exactly how you did that.
How that? What was the
Because-
first one?
9
9 of hearts. Yes,
What's the second one?
No.
Not a diamond.
What was the third one?
You ain't fooling me with this one. I've actually seen this on TikTok, kind of. You knew what the last one was gonna be. You knew what the last one was gonna be. So you said 9 of hearts. But the first one, you picked it up, you saw what it was, and then when you guessed the second one, you actually said what was already in your
That is
hand.
actually correct.
I know.
That is how you do it.
I
Card
know.
card is this. Alright? How do I know what this card is?
You just do. You're just doing this. I don't know.
You're right. I know what this card is, but
But-
instead of pulling this card, I named that card here.
Yeah.
But then when I pull this card,
You name that.
I
for
named
the
this
second.
card here.
Yeah. But
Right?
how do you know what that
So this card, I named the 9 of spades. this card I named the Jack of Diamonds.
This
card I named the 4 of Diamonds.
Yeah.
I end up with all 3 cards.
So, but how do you know that last one? Tell me, please.
A great magician
You
never
just looked it
tells
up on
their tricks.
TikTok, don't you know?
No, because they, it wasn't cards. It was like they did it to their little elementary school kids or whatever.
Hey, make a bunny come from your head.
You don't have to have.
That's my favorite.
Yeah. What he said, I'm not ready. Rain come on the damn trash can.
All right.
He
Okay,
probably
terms
like
mutually
setting his body
exclusive
up
versus
in the
mutually exhaustive.
Sadly, yes.
If events are mutually exclusive, they cannot occur together. So probably A and B equals 0.
Right.
If events are mutually exhaustive, event 1 or event 2 must sum to 1. So flipping a coin is both mutually exclusive, heads or tails, and mutually exhaustive. One or the other must happen. Rolling a die can't, well, depending on how it's listed, can be mutually exclusive, but doesn't have to be mutually exhaustive. So I said before the break, a couple of you were working out, right, if I roll what's probably rolling a 3, or probably rolling a 5, right, those are mutually exclusive, but they're not exhaustive. They don't cover every case. Probability of 3 is 1 in 6, the probability of 5 is 1 in 6, probability of 3 or 5 is 2 6, 1/3, 0.33.
Is this where the with or without replacement comes in?
It's the next one. This is not with or without replacement yet. But that was in the next one.
But can that change whether it's
Not in this case. The
exhaustive?
terms mutually exclusive, mutually exhaustive are entirely separate from each other.
Oh. I thought I was on something.
If there's an addition rule, there's also going to be a multiplication rule.
Is that for the and?
This is going to be the probability of A and B.
Okay.
And, I'm going to draw a little line through all this. Like that, right? So for the multiplication rule, probably A and B, there's a generic rule, and then there's going to be a specific rule, just like the addition rule. This one's generic, this one's specific if they're mutually exclusive. Right? So the generic rule, the broad multiplication rule, probably A and B is equal to, watch the language here, watch the notation because it's going to be a little bit different. I doubt any of you have seen it before. Right? Probability of A, just like we had before. Right? Notice it's a multiplication rule. The word and is going to equate to multiply. So if you want to put a little multiplication symbol like a dot or a little X, you can, but I wouldn't. Just leave it straight up. Probability of B, and this is the weird term, there's a straight vertical line, A.
But that don't mean divide, do it?
That does not mean divide, this is not fraction. That's the point.
I know what that means, I just don't remember. So I don't.
This translates as the probability of B, given that A has already occurred. Probability of
Wait,
B,
repeat that.
the vertical line here, translates as given that
Okay.
the event after the vertical line has already occurred. So the probability of A times multiplication rule, probability of B, given that A has already occurred. Right? We've already done this a few minutes ago when I did things like I
Is
said,
that
what's the
in Brazili's?
Hmm?
Latin for post. It's like in Brazili's. That's the pizza place, ain't it? A poster los
Impellizzari?
See?
Oh.
And no, that's the name of the individual who actually opened the franchise decades ago.
Given
The,
that.
No, I'm
the
saying you
individual,
just
the
told us
family
A
sold
priori
it
occurred.
You
about
told us
20
a
years ago.
prior.
A priori
Thank
versus
you.
a posteriori.
That's what I was trying to say.
Impellizzari is the name of the Italian who opened the pizza place in Louisville.
I'm getting it. It's Italian, right?
So if I say what's the probability of, let's say, in 2 draws, notice I can't do this in a single draw. What's the probability of drawing an ace, let's say of diamonds, let's make a diamond symbol, followed by an ace of diamonds, right, without replacement.
Oh, 0.
Okay, wait.
If it's without replacement,
Yeah.
then you can't draw the first one and then the second one.
Okay,
Yeah.
0 there. If I change that and make it a king of diamonds,
Okay.
Okay.
without replacement, right? Probability of, we'll say ace diamond, times probability of king diamond, given the ace is already gone out of the deck.
That does not make any sense.
I don't.
Sure it does.
Oh wait, yeah, because then it changes it out of 51 instead of out of 52.
There you go. Probability
Yeah.
of the ace initially is 1 over 52. Notice this is actually a fraction. Times probability of the king. But how many king of diamonds are there?
Oh, that's what the
4.
The 1.
Okay.
But there are only 51 cards because the ace of diamonds is already gone.
Yeah.
Alright? This type of notation,
What?
you're going to have to pay attention to
She said,
how
what?
many objects meet your required event,
Okay.
and the denominator, how many total objects are there.
Okay.
Right? So if I were to ask, what's the probability, let's go ahead and extend this a little bit, without replacement, what's the probability of drawing an ace of diamonds, and a king of diamonds, and a queen of diamonds, and a jack of diamonds, and a 10 of diamonds, which would be a straight royal flush if you drew it.
Yeah, so it would be 52, 51, 50, 49, blah, 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 and it would go down, right?
With each card,
It would
without
just be a lot
replacement.
of multiple.
How is this fair for people who don't know cards?
You said you did.
I take that back. I don't know them this well. To be doing math problems.
Yeah. Please quit. Why did you just keep writing
It's like when you're making a poster in like elementary school and you start writing in the middle and then it gets really small.
Yeah. Because you're running out of
When you
space.
start too big and then you're like, uh-oh.
I shorthanded here. So if you're going to draw the ace of diamonds first, the ace is now gone. Now you got to draw the king. There's a 1 in 51 for the king. There's a 1 in 50 by itself for the queen. Right? There's a 1 in 49 for the jack.
No.
There's a 1 in 48 for the 10.
Where's the jack?
I will not do
There.
that.
Jack of diamonds, given the ace, king, queen have already been gone. So there's the given line here. Given ace, king, queen have already drawn. So the queen, given the ace and the king are gone. Right? Make sense?
Yep.
That's not actually a probability of a straight royal flush, but it's close. Right? For example, if you're going to use straight royal flush, that could actually occur in diamonds, or spades, or hearts, or clubs.
So like,
So that's multiplied by 4 because they're 4 different suits. And when you're drawing them out in a deck, right, you don't care about the order. So you don't care if you got the ace first, the king first, the queen first, or the jack, or you might get the jack and then the queen and the king, right? The order here doesn't matter. So it's not quite, but it's incredibly low odds given your multiplying events.
Don't erase anything. This might take a while.
This is going to go on the end there. All right, so you have 5 events. First event, second event,
So you can have
third
like
event, fourth
unlimited
event.
number of events, you just have to plug
Well,
them
if you're
all
dealing
in.
with a deck of cards, you've only got 52 possible
Yeah.
events because once you're done with it, you're done with it.
But if we're not talking about cards, just with the multiplication rule in general, you could just
You can concatenate more than one event.
Yeah.
So, for example, technically, while I got A and B is probably A and B here, the way I did it over here with the straight roll and flush, that's probably A and B and C and D and E,
oh my god.
right? Where the A is the ace, the B is the king.
Does the book explain this pretty well?
Yes. And the book uses a bunch of card examples too. That's why you need to know the cards, deck cards. Like I said, decks of cards are really good for these types of examples because they lend themselves very neatly to fractions, and they're not multiples of 10 because they have 52 cards in the deck. Assuming you know it's a standard deck. Anybody put pinochle?
Peanuts.
How many cards are in a pinochle deck?
Peanut.
Oh, I've seen it played, but I'm not familiar with it.
48.
Peanut.
Is that just the deck without the face cards?
No, it actually does. Well, it's a deck that has exclusively face cards, aces, and I think down to 8s. But it doesn't have any lower numbers. And every card is every card of every suit is represented twice in the deck.
Yeah, I've seen
I know you don't like
older
computer.
people play it,
You
but I
would really
don't.
like the game Balatro if you haven't played it. It's like it's like solitaire and like poker hands if they had a baby. It's kind of fun.
Okay with this idea?
Nope.
Main point here. Here's the main take home, right? This is a multiplication rule.
And
2 events, and if you see the word and, you're multiplying.
not
If you see the word or, you're adding.
Daddy.
that's
You
what
might
makes
be
it
subtracting
confusing.
if they're mutually exclusive or not.
That's what makes it confusing, the and the or, and you automatically think addition, given your grade
Or
school
is
math.
addition, and is multiplication. 2
Exactly.
events occurring together, right, is multiplying probability.
Cool.
Yeah.
It's calculator does not.
Just
do
like there
cards.
is a special case for the addition rule, there is a special case for the multiplication rule. So let me give
They
you an
have to
example.
equal 0, equal 1. No. Yes.
Term here comes up as
Can you use this in darts?
now you could do it if you were throwing darts randomly. If you assumed every dart throw was random and hit the board, you could then use this kind of stuff. Odds being 1 in 20 hit any given number. It'd be much more difficult to calculate the odds of the doubles or the triple space. But you could do it if you just had 1 in 20 and assume the darts were random, right? Instead of being based on skill and accuracy. Yeah, one of the things you have to. Let's talk about a term real quick. Let me do this, and we'll talk about term. I didn't mention that term. All right, so term here is independence. Two events are independent of each other if the probability of one does not change the probability of the other. Be very careful. Do not confuse independence with mutually exclusive. They're two entirely different concepts.
Give us the definition. Two events are independent.
Two events are independent if the probability of one does not change the probability of another. Notice, if you have a series of events without replacement, right, by definition, they are not independent.
Okay.
Right? If you have events with replacement, they are independent. Right? Sometimes people confuse those terms, right? In the case of the cards, right, if I do it without replacement, so I take a card out, it's gone out of the deck, right? It goes from a 1 in 52 to a 1 in 51, right? If I take another card, it's down to a 1 in 50. Take another card, it's down to a 1 in 49, right? Taking the first card out changes the probabilities for every next remaining draw. So those events are not independent. The later draws are dependent on the earlier draws in terms of what was taken out, right?
So without replacement makes it not independent.
No, without replacement makes it independent.
What?
Make sure that
No.
gets it backwards. Without replacement means events are not independent.
Okay, that's what I thought.
That's what I said the first time. Right? Independence means the probabilities don't change. So, great best example of independent stuff. Suppose I have a die, right? I roll a die, I get a 2, right? I'm going to roll a die again. Given that I just rolled a 2, there's a given, right? What's the probability I roll a 2 again?
1 out of 6.
1 in 6. Did the odds of rolling 2 the second time change because I rolled the first time?
No.
Those events on the die are independent, right? You don't tend to think of it this way, but you can. When I roll a 2, I replace the 2 on the die. I didn't take the 2 off. It's not like the die becomes a 5-sided die when I roll once.
Yeah.
Well, the deck of cards, when I take a card out, it's a different deck of cards than I started with,
That makes sense.
right? If I roll the die multiple times, the numbers keep staying on the die, so they're being replaced consistently every time I roll a die. If I take a deck of cards with replacement, so I take a deck card out, put it back in the deck, right? Events are now independent of each other, assuming I randomly shuffle between draws. Right?
So without replacement means that events are not independent.
Correct.
Mm-hmm.
Independence, here I'll put it this way, with replacement. With replacement. If you have independence, for the multiplication rule, probability of A and B is equal to the probability of A times probability of B. Because there is no given. The given doesn't matter because everything's back where it originally started. All the probabilities stay the same across all draws. Right?
So that just saves you a step if you understand it.
It simplifies the rule.
Okay.
All right, that's why I said this is the generic rule. This is the simplified rule, special case. In the same way that knowing mutually exclusive simplifies the addition rule. Does that make sense? All right. Any questions on the basic rules? Let me move those over so I can have some border space, and then we'll change things around a little bit. So. Oh, I was going to mention another term. It's an important term. We've already had it early in class. We're going to have it again here. I'll put up my terms first. as 0, because the probability of A and B is equal to 0 if they're mutually exclusive.
So do these count as formulas? Like
Yes, these are the formulas.
Okay.
So those are the 4 basic formulas. Like I said, they're easy formulas. Right? The hard part is translating the verbal question in English into a formulaic representation. The hard part is representing what the probabilities are a priori if you know them. Right? You have to recognize the probabilities underlying as a priori known probabilities.
And so we will be replacing these with numbers for the exam?
Yes, we're going to do some examples of the types of problems you're likely to see in this area. Okay?
And is that if mutually exclusive or exhaustive in
That is mutually exclusive to change the rule. Mutually exhaustive won't actually change the rule. Although you kind of recognize that if 2 events are mutually exclusive and mutually exhaustive, those events' outcomes must sum to 1.
So then you could just minus 1. No?
I don't know if you meant minus 1.
I thought you meant that if they were mutually exclusive and mutually exhaustive.
If they're mutually exclusive and mutually exhaustive, the special case of the addition rule equals 1.
Okay, okay, I see.
The probability of A or B equals 1.
Okay.
And that's actually going to be the case next week. Well, I'll probably get to it tonight with the binomial distribution.
Are you gonna have like another study session?
We were fortunate to have the spring break opportunity in which to do that.
So I gotta take my leave.
Oh, that does raise an interesting point too. I may mention this again next class. It is perfectly fine to get tutoring outside of the class. Right? I would caution you, if you are getting tutoring outside of the class, to encourage your tutor to use the same formulaic representations we're using in the class. If you go out online, or you go out and talk to a tutor, and they walk you through stuff, right, and they use a variation of the formula, right, when you get the formula page that I'm going to give you, the formulas may look different. Doesn't mean your formula is wrong, because there are different ways you formulate things, but it becomes confusing if you go and look at and you think, well, wait, this is not what I learned from my tutor. That's because I didn't teach that version of the formula. There's at least one person on the second exam that used a version of the formula that I did not teach you. Which is fine, right? But it makes me wonder where you got that formula from, because it doesn't show up on the formula page. It's not one I talk about in class.
But they still got it right, so.
It's still the correct formula to use. I don't know if that individual actually got the math of that problem right or wrong, but they had technically the right formula, but not in any formulaic representation that I taught. And I know it well enough that I recognize it. See how it's the correct formula.
Photo math.
Huh?
Chat GPT.
Khan Academy.
No. They were, let's put it this way. It is obvious they were learning with someone else's help, because whoever was someone else knows it well enough to recognize the variation from the formula. And they said, here, use this formula instead.
It worked for them.
Yeah, be careful with that, because that can sometimes be more confusing than it is helpful. But if that works for you, that's fine. That's like I said, for example, the correlation coefficient. There's a different way to represent that formula than I represent a Pearson product.
My tutor likes to look at the book, at my book first.
Well, that's a very strongly recommended thing. Whenever I've done tutoring for other people in other classes, yeah, flipping through the chapter and reading the chapter tells you how that particular author presents that.
Yeah, I gotta get her my book like before our session, and she gotta. That's why she charged so much. But she's been helping me, because I don't get it when I leave here. Never do.
She said never do.
Gotta keep my job.
I think you're getting more than you think. I think it's coalescing by the extra touches.
Mm-hmm.
All right. Any questions on addition and multiplication rules? All right. So term that I've used multiple times at this point. I'm going to specify here. Random.
Uh-oh.
The use of the word random has a very specific meaning for our purposes. Right? People use the word random every day in the colloquial, common sense use of the word. Frequently wrong, and it annoys me when people use the word random in weird, inappropriate ways.
When they say that was random. Do you know what random is?
Like, Shelly, would you be able to use? What would you be able to use to calculate the probability of a tornado?
We'll come back to that. The question for weather events, right? We'll come back to this. This is a very good question, right? The bigger question, not necessarily for tornadoes, when you watch the news and when you get your feeds on your phones for weather alerts and kind of stuff, right? How do the meteorologists involved put percentages on outcomes? It shows up every day in terms of storm kind of stuff.
Like
right?
70% chance.
There's a 70% chance
Yeah.
of rain, or there's a 20% chance of rain, or there's a 15% chance the winds are going to be over 40 miles an hour kind of stuff. There are a lot of ways to do that. I can mention a couple of them in a second. Anyway, term random. Well, since we're segueing on that topic, the weather is not random, okay, at all. Random means, right, for every possible event, taken from a group, each event is equally likely. For every possible event, those events are equally likely.
That's what random means?
That's what random means. Which means I'm doing something like rolling a die, and I've got 6 possible events on a 6-sided die, either a 1 or a 2 or a 3 or a 4 or a 5 or a 6, right?
Okay.
Those events are random, right? If it's a fair die, they should all be 1 in 6. As the die gets used, right, well here, let's do it this way. All right, a couple volunteers. Who's going to volunteer?
Me.
All right, you're my first volunteer.
Okay.
Write these numbers down. This is a 6-sided die.
Okay.
Right? Write these numbers down. All right, so roll a die. I got a 4. Even numbers? I got a 6. I got a 4. I got a 4. Whoop. I got a 2. I got a 2. I got a 3. I got a 4. I got a 3. That's not rolled. There's a 2. There's a 5. It's actually going to be nervous. There's a 5. How many of you have I rolled so far?
1, 2, 3. 12.
Oh, let's do a few more. There's a 4. There's a 2. There's a 4. There's a 3. That should be 15.
Yeah, I think so.
You did not roll a 1 a single time.
No.
Set that die right there.
Oh gosh. Okay.
Same thing. Who's going to keep track?
Not me.
Go ahead.
Oh, Greg did it for safe one.
Track. 4. 1. 2. 1. 4. 3. 2. 1. 2. 3. 1. 3. How many of that so far?
12.
Do 3 more. 4. 2. 4.
Someone skewed towards low numbers? You got some
Third
trick,
die.
You got some trick dice, don't you?
Do you really? Do you? Are those trick die? Are those
Oh,
real?
that trick. That's dice. There you go.
Yeah, I didn't like that.
5. 1. 6. 2. 5. 2. 4. 1. 4. 1. 4. 4. 4. 6. 1. Is that 15?
Can I make a guess?
All right.
Can I make a guess? Skewed towards high numbers, skewed towards low numbers, regular dice. Die, whatever.
Close.
Close?
That's a fair die.
Yeah.
Every number is represented equally on that 6-sided die. Now, granted, I only did it 15 times. Notice that's a posteriori, right? If I kept rolling this die over and over again, 10,000 times, 12,000 times, right? Assuming every number comes up equally, it'll come up relatively close. Every number will come up the same number of times in a longer sequence, right?
Right.
As you correctly pointed out for this die, right? We never rolled a 1 on this die.
No.
Is there not a 1 on that
There is
die?
not a 1 on this die.
Oh.
It has 6 sides. 2 of them are numbered 6.
So that's what it means.
Which is
by
crazy
saying
though.
something's
Which is
wrong.
crazy because it rolled so many 4s.
Yeah, you only rolled 6 one time
Damn.
I know.
out of that whole. Oh, that's crazy.
This is what random means.
Interesting.
Right? Just because things are random does not mean you're guaranteed
Yeah.
to get the a priori probability.
Is
Yeah.
that
But with extended numbers, you will. I only rolled it 15 times. If I rolled it 1,000 or more times, it'll be closer, and the 6 will show up twice as often as the others.
is that
For this die.
0.001 thing you were talking about when
Yeah.
you said something's wrong?
Pretty much. For this die, while it does not skew toward the lower numbers, it does in the sense that there are 2 1s on it.
Oh.
Right?
And how
Or
many
no
ones did he
sixes.
roll?
And no 6s. This die has no 6s.
Okay.
Right?
Mm-hmm.
A priori, you would expect each number to come up 2.5 times in 15 rolls.
Did it come up 2.5 times? No, I'm just kidding.
Well, it's not going to be a half.
Obviously, that's a
Yeah,
joke.
those dice are not loaded, but they do have 6 sides, but they do indicate numbers. If you keep getting events like that, and the probability of the results is so astronomically small so as not to represent your a priori conclusions,
There's something
this is
going
important, given they're random, right? You know what the random outcomes are. You can calculate a priori if events are up and up, if events are not biased, if events are fair, every event has an equal probability of occurring.
Mm-hmm.
That's what random means.
And we'll be able to tell that in a word problem by.
You will make the assumption for all the problems that events are random if we're doing things like fair dice, things like cards out of a deck, shuffling the deck up, right? If you're doing things like rolling dice that are not 6-sided dice, right? You're going to assume that the dice are fair. All right? And usually I'll say events are random in some sense. There are other kind of ways to set it up.
Okay.
So if you're doing, here's how you get random. Fair die rolling produces random. Notice there are multiple ways of rolling dice: 4-sided, 6-sided, 8-sided, 10-sided, 12-sided, 20-sided, right? Plus any number of others. The others are harder to make, so the geometric shapes get weird. But you can have like a 7-sided die if you want. But they're incredibly rare to use. But anyway, flipping coins, typically random, right? Effectively random. Flipping coins is not actually random, right?
Because it's got to be either or, right?
Well,
Every
either
time.
or, they will sum to 1 how many heads you get, how many tails you get in a given long sequence of flips will not exactly hit 50-50, right? Most coins in the American styles, like pennies, nickels, dimes, quarters, will tend to be just fractionally weighted toward the head side, so you're more likely to get tails because the heads will show up at the bottom 1 out of 10,000 more often. So if you flipped a coin 500,000 times, right, you'll get slightly more tails than you will get heads because there's more weight on the coin on the head.
Before the Super Bowl.
Hmm?
I want to do football players know that.
I have no idea if the coins used in the Super Bowl are weighted or not. They're effectively random. For the purposes of only 1 or 2 flips in a single instant kind of thing, they're fair. If you had the same coin flip 1,000,000 times,
Each
right,
time it gets
you would
more.
notice where the discrepancies are.
Gotcha.
Okay.
But it would take 1,000,000 times to show the difference.
Okay. Thanks.
Coin flipping are effectively fair. Pulling out numbers out of a hat, right, like lottery, ping pong ball numbers. That's fair. If they're bouncing ping pong balls around, right? They're
Like
fair.
little bingo spinner.
The bingo spinners tend to be pretty evenly fair. They're basically drawing lots is what that's called. Drawing lots in most formats tends to be relatively fair. Do not think that you as a human being can generate a random string of numbers, because you will not be able to generate a random string of numbers. Your brain does not work based on random processing.
We like patterns.
Really?
Yes, really.
He said that in one of the classes last semester.
So our brain just already
Now, give a
know
good
what
example,
numbers we
too.
want?
Huh?
Our brain already knows what numbers we want? Are we biased?
Your brain will tend to be biased toward particular number representations, particularly when you use a base 10 system and you use 0 through 9, 10 digits. Your brain will tend to gravitate towards specific outcomes. I have no idea. If I had to guess, probabilistically, either a 7 or a 2.
Nope.
What?
It was a 7.
He like, people are idiots.
Mine was a
If it were entirely random,